Hello friends, welcome to my channel. Let's have a look at problem 2095, delete the middle node of a linked list. So in this video, we're going to present a standard method for locating the middle node in a linked list, the so-called slow fast pointers. So first I'll read through the statement and then we analyze the problem and finally we share the code. So first let's look at the statement. So we are given the head of a linked list. Then we want to delete the middle node and return the head of the modified linked list. So here are three examples. So we are going to look at the first two because they demonstrate the generic cases. So in example 1, the length of the linked list is 7, and the 7 is an odd number. So in this case, the middle node is the node with value 7. So after deletion, so the node 4 will point to node 1. So the result is 1, 3, 4, 1, 2, 6. So this is example 1. So in example 2, the length of the linked list is 4. So according to the problem requirement, so we're going to delete node 3. And after this deletion, so node 2 will point to node 4. So the result will be 1, 2, 4. So that's the two examples. And also let's look at the constraints before we do the analysis. So the first constraint is on the number of nodes in the linked list. In other words, the length of the linked list. So it's in a range from 1 to 10 to the power 5. So 10 to the power 5 actually is a decent large number for the length. The second constraint or assumption is on the value of the node. So the value is in between 1 and 10 to the power 5. So the second constraint or assumption is not that essential for our solution here. So with that said, let's look at the method and analysis. So the method is standard, the slow fast pointers. So basically the key for this problem is to find the middle node in the linked list effectively. So for this, actually we can initialize two pointers. One moves slow and the other moves fast. And the one moves fast moves twice as fast as the slow pointers. Then the effect is that once the fast pointer arrives at the end of the linked list, then the slow pointer will locate the middle of the linked list. So that's a rough idea, right? So after we located the middle node in the linked list, so we just need to make the previous node of the middle node point to the immediate successor of the middle node. So that's the idea and the general procedure. So for this problem, actually there is an edge case. So that is, if the linked list contains a single head node. In other words, the length is 1. By the requirement, the length is at least 1, right? So if the length is 1, then after deletion, the linked list will be none. So we need to pay attention to this edge case. So next, actually, we can do the coding. But before we do the coding, so here is an extension. So can you use this method to detect possible cycles in a linked list? So this actually is also a typical question. So it's good to practice. So with that said, we are ready to look at the code. We're going to delete the code into divide the code into several parts. So first part is going to treat an edge case. So in this case, so basically if the length is just 1, then after deletion, the linked list will be null, right? So if not head next. So in this case, we just delete the head itself. So we are going to return none. So this is the edge case. And then we're going to do the generic case. So the thing is that we want to locate the middle element node and then adjust the pointer, the pointing, obviously. So we will do this in one go and finally return the head node. So once the linked list has length greater than 1, then after the adjustment of pointing, we just need to return the original height reference. That's the overall thing. So for this, because we need to track the previous node of the middle element, so we're going to initialize a variable called previous. First, we make it now, and then we're going to initialize 2 pointers. One is slow, one is fast, and initially they are the height. And then we're going to do the standard while loop, while fast and fast next. The reason we write this logic or condition in the while loop is that each time we want to move the fast 2 steps, but we want to just move the slow 1 step. That's why the slow and fast names. So with that said, so what we're going to do is that first we're going to adjust the previous to be the slow, and then we move slow to slow next, to this moving slow 1 step, and then we're going to move fast 2 step next, because fast next is a valid node, so we can call it next, right? So this way, actually, the final state of slow will be the middle element we want to delete, right? So once this done, so we're going to do the adjusting, right? So maybe let's first do this. Copy this part here to make it more precise. So let's use this one as 3. Adjust the pointing. So for this, I will also consider 2 cases. The first case, if slow next, so then in this case we just need to let the previous point to slow next, right? So previous next equals slow next. So this is the one case. So here is an optional step, so we can actually break the link, so slow next to be now, or if you prefer, you can just ignore this line. So this is one thing. Another thing is, if slow next is now, so actually we can just previous next equals now. So this is actually a very very detailed writing. So actually, no matter what, you can always set slow next, previous next equals slow next, because even previous next, slow next is now, so this is still valid. But let's keep in this format. And finally, we're going to return the head. So that's actually a full solution to this problem. So let's first do a special case check. Yeah, it passes example 1, I guess, or modification. Now let's do the generic case check. Yeah, it passes all the generic cases. So I guess, so that's about it for this solution. So this solution actually consists of the following 3 parts. So first, we treat the edge case, and secondly, we locate the middle node, and then finally, we do the adjustment of the pointing. So with this side, actually, this is the end of this video. Thank you very much.